Okay, let me talk about the Rayleigh-Benard instability. The Rayleigh-Benard instability setup is basically, I initially with a temperature gradient at the bottom is hotter, and at the top is colder. So just like a boiling water, the water, you can see the bubble doing this motion, and we'll have similar things happen, and we will derive it in the detail, in relatively detail. The coordinates like this: x, y, and z. So z we consider as uniform, so we don't worry. We're not worrying about it. Um, for the detailed derivation, it's been offered by and I found a really good set of videos, like 5 videos, like 50 minutes each, by NPTELHRD. Um, yeah, I will link on the description first. So let's look at the overview. We have a set of equations. It's basically the fluid equation: zeroth moment, first moment, second moment. So continuity, conservation, momentum, energy equation, and we impose the incompressibility of the fluid, and we assume that it's the fluid it just have. You can assume it expand over over what we basically the density is lower once the temperature is higher. Basically, it expands in a sense. So beta is a coefficient of thermal expansion, and we use those two conditions, plug into this equation. We'll have this expression where kappa is a heat. I assume is a heat conductivity. Let's just. So for zeroth order, we for the zeroth order, basically the steady state, we assume that the U total is a constant. By constant, I mean it's not variable over space or time. And anything is steady, so there's no change over time. So the d over dt is 0. So we'll have this expression, and to solve this is basically like this, which is trivial, and the velocity is 0 at steady state, and the temperature is just a linear growth from here to here. For the first order, we basically make u equals u naught plus u1, and plug into this equation and subtract this. We get the first order. There's a continuity equation. That's conservation of momentum on x direction, on y direction, and the energy equation. So we did some manipulations. Just for detail, you can look into the video. You just do the derivative with respect to y on this equation, derivative with respect to x on equation 3, and then this minus this, and then the whole thing do the derivative with respect to x, and utilize the continuity equation. We ended up having this equation, and we just use equation 4 here. So we ended up having two equations with two unknowns. Unknown is T1 and V1. V1 is the perturbation on the y direction, velocity perturbation on y direction. So, and we make a guess of the expression looks like this, and we define the big D square is d square over dy square, and we plug everything into those two equations. We ended up having this expression. So for the critical point, I mean this equation we can decouple it. We could decouple it, but it will make our life much easier, considering theta equals equals 0, it will give us a certain level of symmetry, as you can see. So we assume at the critical point is sigma is 0. Then we combine those two equations and arrive to this equation, and we notice the rho naught over nu is 1 over mu, which is a kinetic and the mu is kinetic. Sorry, this is nu is a kinetic viscosity. Rho naught Cp over kappa, that's 1 over alpha T, which is alpha T is the thermal diffusivity. And we can make everything dimensionless. D star is defined as HD. H is the distance between the upper lower boundary, and the alpha star is H alpha, and then we define the Rayleigh number is as such. Then this expression is greatly simplified to this equation. We have this, and we know that at the boundary that T1 is 0, and the V1 is 0 on the boundary as well, and the derivative of that is 0 as well, and utilize all that. You can look at detail in the video. This expression satisfies all 6 boundary conditions. This is the 6th order differential equation. And plug that all in here, we have this expression. So this is a Rayleigh number with n with a discrete integer. If we plot the RA, a Rayleigh number with respect to alpha star, with different n, say n equals 0, n equals 2, it's like this. The line is basically the line where the sigma is 0. Below that, intuitively speaking, you can see this. So the bigger, the stronger the gradient, the stronger the gradient is, the more violent the convection or the instability will be. In other words, if RA is bigger, it's more likely to be unstable. So along the line of division, below the line is stable, above the line is unstable, which makes sense. If there's no difference, barely any difference, then there is no convection, because it cannot even overcome the gravity. If it has so big of a difference, then the so big of a temperature difference, then it will have a bigger convection effect. So yeah, maybe with further investigation or maybe numerical calculation, we can have this plot, which is x-axis is a Rayleigh number, y-axis is V1. It's V1, and basically before a certain point, there's no V1, so it's in a steady state. And once it surpasses RAC, a critical point, it will start to become unstable. This line, basically above the line is stable, below the line this here is unstable, and this line is scaling as the square root of RA minus RAC. And just for the context of a plasma physics, potentially you can consider the gravity as magnetic tension and magnetic pressure, so that the magnetic field is basically acting like a pressing gravity, just like the one that we discussed on the Rayleigh-Taylor instability. And just to repeat myself, on the description there's a note and 5 videos about the Rayleigh-Benard instability, full derivation, which I think is very helpful.